Hello students and welcome back to this channel. So in this video we are going to be handling or starting the theory part of organic chemistry as applied to practicals. So this video is presented to you by Yusuf, and your advice to share the video to your colleagues and subscribe to the channel so that we can all benefit as a family. Now when you're handling practicals, we are going to go step by step, just like the way we say it or we make the question flow. So first we are going to start with texture, then later we are going to go to solubility, and then later we are going to look at individual reagents and how they can be used in the laboratory. So after this video we anticipate to make a practical to implement all what you are going to cover in this video. So first we are going to start with the texture or the appearance of the organic substances that can be distributed before we begin our experiments. Then later we are going to handle solubility, and then later we handle effect on the litmus paper, and then later we handle how each and every reagent is going to be treated with our substances that must be distributed in the laboratory. So first, if I just said an advisor, you are supposed to have a summary of practicals. Just like you have a summary of theory, you're also supposed to make a summary of practicals so that you have the theory ready. When you go into the practical room, you are just writing what you already know. So practicals are there to prove your theory, which is already profound in your head. So this video is a basis for you to get a summary or to summarize important aspects and how you are supposed to present your observations together with your deductions in an appropriate manner. Now, starting with the texture or appearance of the substance, we are going to make a table. One is going to be observation and then deduction. Say if at all you have observed that the substance that you are being given is a solid compound, for example a solid powder. So in organic chemistry we assume that all compounds, all carbohydrate compounds, they exist in solid state if at all they are having a high carbon to hydrogen ratio, and mostly those are going to be aromatic compounds, or they are going to be aliphatic compounds. By aliphatic I mean linear. By aromatic I mean compounds that contain a benzene ring within their structure. So if at all we are given a solid substance, we are going to anticipate mainly an aromatic compound, or we are going to anticipate an aliphatic compound with a higher molecular mass, or with a long chain, or with a long hydrocarbon chain. But mainly when you're writing a deduction, you're not supposed to give two alternatives. So you simply say one or two, but mainly it's advisable to give one option, because the more you give options, the more you reduce your accuracy. So someone can say, under observation, that I've been given a solid compound, and then you deduct it's an aromatic compound. Now we are not going to ask you for the texture of the substance, but it's as a must for you when you're beginning question 2 and question 3 to identify the substance being given to you. If it's a solid substance, you start by saying solid substance, and then you denote or you deduct what you think about it. So a solid compound is that is going to, we anticipate an aromatic compound or an aliphatic compound with a high molecular mass. If at all you have been given a colorless liquid or a substance which looks like a colorless liquid, you simply say when you're starting your question that a colorless liquid, and then in your deduction column, now all liquids, we don't expect anything of liquid to be aromatic, because we say that majority of the things that contain, or substances that contain the benzene ring that we provide, are going to be solids in nature. So liquids are going to be mainly aliphatic compounds, and mainly they are alcohols, although you don't have to cram for that. So I'm going to say that when you're starting such a question, you just say that in the observation column, you just say that it's a colorless liquid, or you just say colorless liquid, and then you deduct that it's an aliphatic compound with a low molecular mass. because we are saying it has a low molecular mass because it's not existing as a solid. Because for aliphatic compounds, some aliphatic compounds exist as solids, but only on condition when they have high molecular mass. So that's why I'm deducting that it's an aliphatic compound with a low molecular mass. Now this one is less commonly observed, but let's also look at it, like pink crystals, which dissolved form a pink solution on exposure to the atmosphere. And this one will anticipate us to expect phenol to be present in such a substance. But mainly the observations that you're going to be using are going to be from these two in the table. Now with that, so we are done with the texture. Now let's go to the part of heating. So when you're heating, how are you supposed to write down your observations and how are you supposed to make deductions about what you have seen? So one, the procedure is going to tell you that to burn a small amount of the organic compound on a small spatula end. Now a spatula end, some of you improperly misunderstood this. For a spatula end, your spatula must not be full of the substance. It simply means that the level at which your spatula stops. So that's where your substance must be filled at. And we are very sensitive on this during mocks because in mocks we consider high accuracy and A level is about accuracy. So some of you, when you're measuring these substances, you overuse a lot of the substance that is being given. For a spatula end full, the level of the chemical you're using, you should just slightly exceed the top of that spatula, but don't make it to have a heap on top of that spatula. I hope you have understood that. This one with the heap is wrong. There you have made like two spatula endfolds. It must just be slightly above the level or the trough of the spatula you are having. So the observation you're going to make, if at all you're burning your substance, let me say that you're burning a colorless liquid or you're burning your solid, which is white in nature, and then the observation you're going to make are going to be according to the following. First of all, we are looking at the flame that it's burning with, together with whether the soot is being formed or the soot is not being formed. So when you're burning, and then what you're burning burns with a yellow non-sweeter flame. Yellow and non-sweety flame, we deduce that it's going to be an aliphatic separated compound with a low carbon content. Now notice that here, for compounds that burn with sweeter flame are always unsaturated. We expect double bonds to be present or multiple bonds to be present in such a compound. So if at all you burn your compound and you observe that you have seen a yellow non-sweeter flame, non-sweet, that means that there is no soot on that flame which you are burning your substance with, we expect that compound to be aliphatic because aliphatic compounds, they have a low carbon content. That's why the soot was not being able to be observed. So we expect that compound to be aliphatic and saturated with a low carbon content. So your observation should be burns readily with a yellow non-sweeter flame, forming an aliphatic saturated compound with a low carbon content. Then now here we are going to mainly look at two things. We are going to first ignore this for a moment because you have removed it out of the syllabus. So you either have two options. You either have this one, the first one, or you have this one. So the next one is going to burn readily with a yellow sweeter flame. Now the color doesn't matter of the flame. You just denote the color that you are seeing. But where we are going to put much focus on is whether the burning is with soot or with not soot, because that's where you are going to make aromatic or aliphatic deductions. For aromatic compounds or unsaturated compounds, they are going to give a sweeter flame, or compounds that have a high carbon to hydrogen ratio or a high carbon content. But for compounds with a low carbon content and they burn with a non-sweeter flame, we expect them to be aliphatic and saturated. So that's why these ones which burn with a yellow sweeter flame, we say that they're going to be aromatic, they're going to be unsaturated, and they're going to have a high molecular, or they're going to have a high carbon content. And you can stop there. Or you can, I say that you give one deduction. Or you can say it is a long chain. We expect a long chain aliphatic unsaturated compound with a high carbon content, and then you stop there. So currently we are going to ignore this section and the next section at once. So when you're summarizing, you make sure that you summarize these two mainly, because that's where your syllabus is copying. Now next on the table is going to be solubility. Now here we have to pay attention especially to the part of solids. In chemistry, before even we begin, we don't have anything that is insoluble. That's never in chemistry, and majority of you lose marks from there. In chemistry, we don't have anything that is insoluble. It's either partially soluble or sparingly soluble. So never write anything to be insoluble. We don't have anything in chemistry which is completely insoluble, but we are having solids that are sparingly or partially soluble. So that's the first mistake, and it's a very common mistake that you all make. So for example, if I told you I've seen a step that by the organic substance that you have got, add 2 centimeters cubed of water and then check. Now also here, let me add a clarifying note about here. Now majority of you fail mocks, practicals of mocks, because practicals of mocks were very strict in accuracy. So if you look at this instruction has told you to add 2 centimeters cubed of water, and then you get your test tube, and then you just pour in water without measuring. If you're observant, we always provide you with a small measuring cylinder to measure those quantities, those small quantities that the question is telling you to use. So make sure that if at all you have got strict conditions like this, especially in mocks and UNEB, you use the appropriate volumes they have told you to use. For example, if at all in UNEB, they may tell you add about 2 centimeters cubed of water. There you may not be specific. You may use about 3 centimeters, or you may use about 3.5 centimeters cubed of water. But in mocks, if you tell you to use 2 centimeters cubed of water, the error in this volume is going to be about 2.2, or is going to be about 1.8. So if at all you didn't measure the water to use and you just poured arrogantly, you are going to get no observable changes everywhere, and that's a very common mistake on question 2, which comes from inorganic chemistry. So you need to be very careful about the volumes that are being given. If you are being told to use 2 centimeters cubed of a given substance, you get your small measuring cylinder and then measure off the 2 centimeters cubed and then put them in a certain beaker separately, and then do the experiment as instructed. So first, if at all your substance is soluble in water and forms a colorless solution after that, now here when you're writing observation, you have to write the initial observation and the final observation. That's how we write observations in chemistry. So first you may have a white solid, or you may have your colorless solution or a colorless liquid. So it simply tells us that your colorless liquid was soluble in water, forming a colorless solution. You give the initial state of the substance we're dealing with, and then later you give the final state of what you have got. So that's why I'm saying that a colorless liquid is dissolved or is soluble in water, forming a colorless solution. Give the initial texture or appearance and also the final texture or appearance. And for anything that dissolves in water, we consider that to be something with a low molecular mass. So we're going to say that polar aliphatic compound. Polar means that something that can easily dissolve in water. Polar, water loving. So you simply say polar aliphatic compound. Now examples, some of you give wrong examples. If you're not sure about the example, you ignore it. It's as simple as that. You just state your observation, because the observation are not given more than 1 mark, however much examples you give. So you just give what you're sure of, that polar aliphatic compound present or suspected present. If you give a lot of examples and one of them happens to be wrong, what you have got wrong nullifies the previous mark that you had got right. Let me explain this. If you had got 2 marks in the beginning, and then we find somewhere and you fail an example, this mark you have failed nullifies another mark. That's how we mark chemistry practicals, simply because the rate at which these exams are leaking out of the examinations board is very high. So many students pass this paper, and if at all we are not so strict with the marking conditions, you'll find that majority of you will be getting distinctions. So to minimize that, any error made is accountable with the correct answer got. Now, for this was observation for those substances that are going to be soluble or that are going to dissolve in water. However, some solids or majority of the solids are going to be partially soluble, but we are still dealing with liquids. So with liquids, we can also see that some may be partially miscible with water, forming a colorless solution, and these ones are going to be still polyaliphatic compounds. I say that these examples, if you're not sure, you may leave them out. Some may be completely immiscible with water, and these ones, anything that is immiscible with water does not tolerate or does not like or does not dissolve in water. So we call those compounds to be nonpolar. We refer to them as nonpolar compounds. So anything that is miscible in water, we are going to name it as a nonpolar aliphatic compound. We are calling them aliphatic because they are liquid in nature. When you go to solids, we shall call them aromatic. I hope you understand that deduction. So looking for solids, this is the observation you're going to be mainly making. So I say that this one is not going to be considered for your level, or it's going to be nullified currently, because we do not have any compound that is completely insoluble in water. Rather, we have compounds that are sparingly soluble in water. So if you're having a substance and then they tell you to get a test tube and then you dissolve it in 4 centimeters cubed of water, which we say that, or which we agreed on, that you're supposed to use a small measuring cylinder for that. And then you measure 4 centimeters cubed of water, you put them in the test tube or boiling tube, and then you shake constantly, and then you see what is going to happen after some time. You're going to see that you're having a sparingly soluble substance in water which forms a colorless solution. I hope you are seeing how these observations are being made. We'll record the initial appearance of the substance, and then we will also take it to the final appearance of the substance. So you should be very, very careful about that. The initial substance here. Now someone may also say that a white solid is sparingly soluble in water to form a colorless solution, for as long as you have mentioned the initial appearance or texture and the final appearance or texture. So the observation there, or the deduction is going to be, the deduction you're going to make there is going to be a polar aromatic compound. So it's going to be a polar aromatic compound such as an aromatic carbonyl compound. But I've told you that if at all you're not sure about the example, just write the deduction only, full stop. And if you're giving examples, make sure that you don't give more than 2. I hope you have understood that. So now let's go to the indicator side. Now the indicator side, mainly here, I'm going to talk about litmus paper and then litmus paper mainly, and then the deductions. Because majority of the schools don't have this. But if at all you are being examined in mocks, that's why I also included these columns. However, they are going to remain the same. So if at all you are recording, if at all they have told you that after dissolving, test the filtrate or whatever the resultant solution on both the blue and litmus paper, when you're recording your observation, you are supposed to state what you have observed on both the blue and red litmus paper. Now, some people say that, or some students say that there is no effect on the litmus paper. That is not a specified observation. We need an observation talking about the blue litmus paper together with the red litmus paper. So that's why if at all you're not having any effect, you simply say that no effect on both the blue and the red litmus paper. Make the observation clear don't just say that no effect on the litmus paper. It's like you used one litmus paper. So you make the observation clear that you use both filter papers and you use both litmus papers, and you realize that there is no effect on both the blue and the red litmus paper. And anything that has no effect on the blue and the red litmus paper is going to be referred to as a neutral compound. If at all the blue litmus paper turns red, if at all, let me say you have got a color solution, or the resultant solution turns blue litmus paper from blue to red. I hope you are also seeing this observation. We set the initial color of the litmus paper together with the final color of the litmus paper. That's how observations are made. So anything that changes from a blue litmus paper to red is acidic in nature. So we simply say that acidic compounds present. And the main acidic compounds we are having in organic chemistry are going to be carboxylic acids. But if at all you have got your red litmus paper to be turned to blue, then we expect amines, because it's only basic solutions that turn red litmus paper to blue. And in organic chemistry, the only things that we're having to do that are going to be mainly amines. So you simply say that a basic compound is present, such as an amine. Now for this we may not now I made a summary of this just because some of you may require, or some of you are good at identifying compounds before doing the experiment. So sometimes you may get a compound, or they may give you a substance, for example, mainly those ones that are in liquid state, and you first test or you first smell on the compound, and then you anticipate the class in which it falls. So mainly amines are going to have fishy smell. I hope every one of you has heard how a fresh fish smells. So amines have that smell of fishy like smells. And then mainly amines, what you need to note here are going to be amines together with the esters. Now for the esters, after giving the instructions for esterification, whereby I give you the concentrated sulfuric acid together with an alcohol and a carboxylic acid, and then you tell you to combine them, and you pour the resultant solution in cold water in a beaker, we anticipate you to smell a sweet fruity scent. So you must hear, for an ester to be formed or for esterification reactions, we must have a smell of which is kinda of sweet and fruity. So when you're making your summary, you should note about the esterification smell together with the amine smell, because these ones are the most evident ones in identifying or anticipating when you're in the laboratory. For phenol, we have a carbolic smell, but these ones require when you're doing the practical together. We can't explain the smells via the theory, but in noting, make sure that you note amines, and you also note the one for esters together with the phenol, and then you ask your teacher about a carbolic smell of phenol, or you can go to your laboratory and you try to smell phenol on the scent it produces. So now after that, we are going to be looking at the purpose of the reagents one by one. Now as we are looking for reagents are very crucial. They are not only important in practicals, but you have also resorted to setting these questions in the theory papers, especially paper 1, where we give you a set of a pair of substances, and we tell you to give a reagent, and you also state the observations for each when that reagent is being used. So first we are going to look at usage of sodium hydroxide together with a silver nitrate solution. So this one is mainly used in testing alkyl halides, those ones that are attached to a benzene ring and those ones that are on aliphatic chains. So the test is going to be that so you're saying that sodium hydroxide and silver nitrate solution is going to be used to test aliphatic halides from aromatic halides. Now remember, according to the theory, if at all you're having your benzene ring and this benzene ring is attached directly to an halide, which can be chlorine, bromine, or iodine, the bond between the carbon and chlorine is very strong. so this chlorine atom cannot easily be substituted. That means that if you're using hot sodium hydroxide solution followed by silver nitrate solution, we expect no observable change on aromatic halides, but we expect observable changes on aliphatic halides. So that's why we are telling you that in the test is that you're going to add the sodium hydroxide solution and then you shake well. And then later you heat the mixture and then allow to cool and then later add silver nitrate solution. Now when you're writing this one in theory, you simply say that the reagent you're going to use is going to be hot sodium hydroxide solution followed by dilute silver nitrate solution. Now here, the observation you're going to get is going to depend on the halide, because the silver nitrate is going to provide silver ions that are going to react with the halide ion that you're having. If it's a chloride, we expect you to get a white precipitate. If it's a bromide, we expect you to get a cream precipitate. And if it's an iodide, we expect you to get a pale yellow precipitate. And that's due to formation of white precipitate is going to be due to formation of silver chloride. The cream precipitate is going to be due to formation of silver bromide. And then the pale yellow precipitate is going to be due to formation of silver iodide. So you need to be very careful about that. So in a noting, like I told you, you need to understand the chemistry of direct attachment of an halide or an halogen atom to the benzene ring. If you use this reagent on aromatic halides, there is not going to be an observable change simply because the bond between carbon of the benzene ring and the halide or the halogen is going to be very strong. So it's going to be very hard for this chlorine atom to be substituted for. That's why we are going to get no observable changes here. And then on aliphatic halides or linear chain hydrocarbons of alkyl halides are going to give observable changes. And you have said that observable changes are going to depend on the halogen attached. If it's chlorine, you're going to see white precipitate. If it's bromine, you're going to see a cream precipitate. And if it's iodine, you're going to see a pale yellow precipitate. So now the next reagent we're going to look at is going to be the iron chloride solution. Now we know that iron chloride solution is mainly used to test for phenol. So with that being said, the test is going to be that add to 1 centimeter cubed of your test solution, you add iron chloride solution. Mainly we are going to tell you drop by drop until in excess. So the observation, in case phenol is present, you must see a purple coloration to be formed. Now there's a difference between a purple coloration and a purple solution. Some of you write purple solution, but that's not a purple solution. Actually, it's a violet solution. It's a violet solution forming a purple coloration, but it's not a purple solution. You need to differentiate the two. So here the right observation, or the most appropriate observation, is going to be a purple coloration to be formed. And if I tell you say purple coloration or a violet solution, then violet is not the same as purple. So you either say violet solution or you say a purple coloration formed. And that one is going to prove to you, or is going to confirm, presence of phenol. And if you don't see any observable changes, then we shall deduct that phenol is absent. Now also, this is to test for phenol. Also, antichloride solution, we use it in testing for the acetate ion. If we use it in testing for the acetate ion, which is always in this format, and this is, you're going to notice this. I think you should put this down in the brackets if you're writing these notes. So when you're adding this one, when you want you to test for this acetate ion, we are going to tell you that after adding that iron chloride solution, you heat. This word must be there. And if at all you are going to use it also in the theory as one of the reagents that is going to distinguish this ion from any other compound, we need to see this condition of heating. Without heating, we are not going to get the desired results. So in a testing for this one, or when you're confirming its presence, you can also use antichloride solution, but this time around, unlike phenol, you heat. And on heating, we are going to form a brown precipitate. And after forming that, you simply deduct this. You say that acetate ion suspected present, or you can say that sort of aliphatic carboxylic acid present. Or simply you say acetate ion CH3COO negative present. This is the confirmatory test of this ion. I hope that is clear. And if you get no observable change, you simply denote that this one is absent. As simple as that. Now, before heating, we expect you to get a red coloration, but this red coloration turns slowly reddish brown on heating. But if you add neutral ethyl chloride solution and heat straight away, you are going to get your brown precipitate, and this is a very common test that we examine in practicals. So you need to pay attention to it. So now looking at another reagent, you're going to look at sodium hydroxide solution. Now for sodium hydroxide solution, we are only going to focus on the first observation or the first deduction. Now these ones, you may surface them in mocks if at all there are any mocks that try to go in details. But mainly sodium hydroxide, when you tell you to apply sodium hydroxide alone, we are testing for whether the substance you are being given is acidic in nature or is alkaline in nature. If at all it's a solid substance and then we tell you to dissolve it in sodium hydroxide and it dissolves, we expect it to be acidic, because in reactions in chemistry, we expect a base to react with an acid in order to form a salt which may be colorless in nature or which may be soluble, forming a colorless solution. So mainly when we tell you to use sodium hydroxide, we are going to be looking at this first option. And like I've told you, you may also note down this if at all for the cases of mocks, but mainly for ENAB, we are going to be focusing on the first test. So the first test, we are going to tell you that get your substance and add 4 centimeters cubed of sodium hydroxide solution. Then you shake until it dissolves. So the observation you are going to give is that when you're giving observation, you start from the initial color or the initial appearance to the final appearance. So you simply say that a white solid dissolves to form a colorless solution without evolution of a gas. Or you can simply stop there, that a white solid dissolves in sodium hydroxide forming a colorless solution. You are going to get 4 marks. And when it does so, we expect that there has been a reaction between a base and an acid. And those reactions, we call them neutralization reaction. So that's why in your deduction column, the first thing you need to write is going to be neutralization reaction, comma, therefore an acidic compound suspected to be present. But which acidic compounds do we have in the laboratory? You know that it's only carboxylic acid. So you simply say neutralization reaction, hence carboxylic acid suspected present. You keep your deductions as brief as possible. Like I said, we are not going to talk about these ones, but you may go through them when you're dealing with your practicals. So now for the next reagent, we are going to look at the purpose of sodium carbonate or the purpose of sodium hydrogen carbonate solution. Now both of these reagents are used to test for the presence of carboxylic acids or for presence of the carboxyl group on any of the substances that are being given in the laboratory to conduct your experiments on. So whenever you say sodium carbonate or sodium hydrogen carbonate, just know that the main purpose of that test or that step is to identify whether you're having a carboxylic acid in your analysis, or whether you're having a carboxyl group attached to the compound you're dealing with in your observations or in your experiment. So first, the instructions are going to be clear. You add a given volume of sodium carbonate solution or sodium hydrogen carbonate solution. They both function the same way. So if at all, what it does, if at all there's a carbonate or a hydrogen carbonate, the carbonate or hydrogen carbonate react with the carboxyl group, and then we give off the carbon dioxide gas. So you expect you to see either bubbles of a colorless gas or effervescence of a colorless gas. But majority of you have challenges with writing this pairing, effervescence. So strictly stick to bubbles. B-U-B-B-L-E. So you simply say bubbles of a colorless gas to avoid inconveniences of spelling, because you are very strict at marking grammar in chemistry. Because you don't anticipate you to prescribe medicine to a patient and then you're writing wrong grammar. You won't be a good doctor. So with that, in your observation, you simply say bubbles of a colorless gas evolved. Now here, we shall know that the gas is going to be carbon dioxide gas. So giving this test is optional. This test is going to be optional. You simply say effervescence or bubbles of a colorless gas, and then you say carbon dioxide gas evolved. After that, the only thing that can give off carbon dioxide gas with sodium carbonate or sodium hydrogen carbonate is going to be a carboxylic acid. So you conclude that carboxylic acid present. I say that you are going to ignore this continuation part when you're summarizing. Whenever you use sodium carbonate and sodium hydrogen carbonate, we know that if at all the gas is going to be evolved, it's going to be carbon dioxide. So there is no purpose of carrying out a test to test for that gas, because there is no other gas that can be evolved when you use those two reagents. Now, in case you don't see the bubbles of a colorless gas or effervescence of a colorless gas, you simply say that it's going to be no observable change. And with that, you simply say that carboxylic acids are therefore going to be present. Now let's look at the 2,4-dinitrophenyl hydrazine solution, which is known as the Brady's reagent in your practicals. Now first we have it when you're testing, when you're using Brady's reagent, we are looking whether you have carbonyl compounds or not. If at all carbonyl compounds are present, for aliphatic, you will expect you to get a yellow precipitate. For aromatic or things containing the benzene ring, we expect you to get an orange precipitate. And like I said, these reagents are very important for you to summarize down, because we ask them both in theory and in practicals. That's why your theory has to be good for you to pass practicals. So you get a yellow precipitate if at all your substance you're having the question is an aliphatic carbonyl compound. So it's going to be yellow precipitate for aliphatic carbonyl compound. But if at all you're having an aromatic carbonyl compound, you are going to form an orange precipitate. I hope that has been well mentioned clearly. So the reduction for that is going to be carbonyl compound present. If at all you have got a yellow precipitate, you say aliphatic carbonyl compound present. If you get an orange precipitate, you say aromatic carbonyl compound present. So you may squeeze that somewhere. Now, if you don't get any of the precipitates seen, you simply say that there is no observable change. And you simply say that, therefore, carbonyl compounds are going to be present. And carbonyl compounds here, we're talking about ketones and aldehydes. Now, like I said, majority of you get no observable changes because you don't follow the instructions. If at all they have told you to add 2 to 3 drops of Brady's reagent, there's no need for you to exceed 5. You simply add 2, 3, 4, 5 and then stop. Have you seen any change? Yes or no? No, carbonyl compounds are not present. Yes, carbonyl compounds are present. Yellow precipitate is going to be an aliphatic carbonyl compound. Orange precipitate is going to be an aromatic carbonyl compound. So looking at the next reagent, we are going to look at sodium hydrogen sulfide solution. Now also, just like Brady's reagent, also sodium hydrogen sulfide solution also tests for the presence of carbonyl compounds. And for a positive test with it, you are going to observe a white precipitate. For a negative test with it, you are going to see no observable change. So you'll be given the instruction that add a given volume to a given volume of your test solution, you add saturated sodium hydrogen sulfide solution. When you see a white precipitate, it's going to be a positive test for presence of a carbonyl compound. And if you see no observable change, it's going to be a negative deduction. So you simply say that carbonyl compounds absent. Now the other thing is going to be ammoniacal silver nitrate solution. Now ammoniacal silver nitrate solution has many functions. First, it may be used to test for unsaturation, presence of multiple bonds, such as terminal alkynes, and also it can be used to test for presence of aldehydes and carboxylic acids such as ethanoic acids, and it gives different observations on each. So if at all we anticipate aldehydes to be present, if at all we anticipate an aldehyde to be present or methanoic acid to be present, we expect we use Tollens reagent. Tollens reagent is the same as silver nitrate solution. Now let me make something clear here. When you're writing practicals, it's okay to write Tollens reagents. When you come to theory, in theory papers, these ones become nicknames. You are not supposed to write them anywhere. Instead, you are supposed to give the appropriate chemical names for those nicknames. So you cannot go to a theory paper and say that you're going to differentiate between methanoic acid and ethanoic acid, and you're going to use Tollens reagent. You will not qualify for any mark, so you'll be losing all the 3 marks on that number. But if you want to get all the marks, then you need to write the appropriate chemical name. So Tollens reagent, instead of writing taurine, you say ammoniacal silver nitrate solution. So when you observe a silver mirror to be formed, that simplifies that an aldehyde is present, or a methanoic acid is going to be present, because methanoic acid has an aldehyde group. If you look at the structure of methanoic acid, is like this. So we expect this one, since methanoic acid has this aldo group, we expect it to give the same observation just like other aldehydes. So ammoniacal silver nitrate solution can be used to test for the presence of aldehydes by forming a silver mirror. So you simply say in your observation column that a silver mirror is formed. If it's formed, the dash you're going to make, you simply say aldehyde reducing agent such as aldehydes or methanoic acid is present. It's only 2, either aldehydes or methanoic acid. So for the next part, we're going to look at Fehling solution. Now, Fehling solution is specifically used to test for aldehydes or simply reducing agents. Aldehydes are reducing agents. So Fehling solution is simply used to test for aldehydes. Now, except one aldehyde, which is benzaldehyde. For benzaldehyde, which is a benzene ring attached to an aldo group. So this one, benzaldehyde, you can separate benzaldehyde from other aldehydes using Fehling solution, because Fehling solution does not give any observable change with benzaldehyde, but it's going to give observable changes with other aldehydes. So that's why I wrote and I told you that test for aliphatic aldehydes, but is going to test for aliphatic aldehydes, other aldehydes other than benzaldehyde, or a benzene ring attached to an aldo group. So for aliphatic aldehydes other than benzaldehyde is going to give a reddish-brown precipitate, and the deduction for that is going to be reducing agent present, and this is going to be aliphatic aldehyde or an aldose sugar. But I told you when you're giving examples, one is enough. So you simply say reducing agent present, such as aliphatic aldehydes, or you simply say such as an aldehyde. So the observation for that, when you use Fehling solution, always, even in biology, is going to be a reddish-brown precipitate. I hope that is clear. Now for benzaldehyde, when you use it, now in theory, when you're using this reagent and you have mentioned it and you're distinguishing benzaldehyde, because it's a very common question, you're distinguishing benzaldehyde from another aldehyde, you simply say, on the benzaldehyde, you simply say an observable change, and on the other compound, you simply say that you're forming or a reddish-brown precipitate formed. It's as simple as that. Now let's also look at oxidizing agents such as acidified potassium permanganate solution. Now we overlooked at this one. in inorganic chemistry series under the videos of transition chemistry. So one of its functions is to detect oxidizing primary and secondary alcohols, detect and oxidize primary and secondary alcohols to their respective aldehydes and also ketones. And also it detects unsaturation and presence of methanoic acid or oxalic acid. So that means that you can separate oxalic acid from other acids using acidified potassium permanganate solution, or you can distinguish methanoic acid from other acids such as ethanoic acid using acidified potassium permanganate solution. And the observation for this one remains the same, purple solution turning to colors. Now let's look at the example under that. So provided for unsaturated, if at all we're having a compound which is unsaturated, so the observation, I say that it remains the same, purple solution turning colors. You give the initial color, you also give the final color. So the deduction under that, you simply say that unsaturated compound with multiple carbon-to-carbon bonds. So it's as simple as that. So acidified potassium permanganate can be used to test for unsaturation or presence of multiple bonds between the carbon-to-carbon atoms. Or it can be used to test for reducing agents such as alcohols and also aldehydes. So you can simply say that also the observation is going to remain the same, purple solution turning colorless on warming. Now you may just stop here, purple solution turning colorless on warming. This one you may not deduct it as, you may take it for your notes, but it may not be required when you're writing your papers. So you simply say that reducing agent present such as primary alcohol or secondary alcohol or aldehydes. Like I said, when I'm giving examples, here I gave you many, but you pick maximally 2. They're enough to write. Now acidified potassium permanganate performs the same way like acidified potassium dichromate solution. So since they perform the same function, here I'm just going to give you the changes that happen because the observations are going to remain the same. So for acidified potassium dichromate, its color changes from orange to green after oxidizing, as we looked at it under the transition chemistry videos. So it's as simple as that. It also tests for unsaturation. For acidified potassium dichromate, it doesn't test for unsaturation, but it may test for presence of reducing compounds or agents such as alcohols, secondary alcohols together with aldehydes. So for it, it's mainly testing for alcohols and aldehydes, anything that requires to be oxidized, but it doesn't test for unsaturation, just like acidified potassium permanganate does. Now looking at this other format, we are going to be looking at ethanoic acid or the esterification reaction. Now under the esterification reaction, you are going to be given an alcohol, or the substance you may have may be an alcohol. And then there we shall tell you to add an acid together with, we shall tell you to add ethanoic acid together with hot concentrated sulfuric acid. Or if you're having a carboxylic acid, we shall tell you to add an alcohol together with hot concentrated sulfuric acid. But the main purpose of that is that we shall tell you to identify that it's an esterification reaction. We shall tell you that after doing all that, you pour the contents of your resultant solution into a beaker containing cold water. Now when you do that, you must observe, or you must observe a sweet fruity smell. And we talked about that under esterification reactions when you are beginning the video. So the instruction, like I said, these ones are going to vary. If I tell you the substance you're having is an alcohol, then you're going to be adding ethanoic acid. If I tell you're having ethanoic acid as the substance in the experiment, then you're going to be adding an alcohol, followed by hot concentrated sulfuric acid. After that, you pour your products or your resultant solution in a beaker containing cold water. The observation you're going to see there is going to be for a sweet fruity smell. Then after that, the reduction is going to be for a esterification reaction because it's only esters that give us that smell, sweet and fruity smell. So I simply say that a esterification reaction, therefore, primary, secondary, or tertiary alcohol present. Now we are saying that, like I said, you give either two examples. You may just say primary or secondary alcohol present. But here, if at all we told you to add ethanol, then the observation or the deduction would have changed, because there you anticipate that you're having a carboxylic acid. So you simply say that a carboxylic acid is suspected present. Like I've told you here, you just have to be aware that this reagent structure is going to change. If at all in the experiment you're having an alcohol, we shall tell you to add a carboxylic acid together with concentrated sulfuric acid. But if you are doing the experiment you're having a carboxylic acid, then we shall tell you to add an alcohol together with concentrated sulfuric acid. You have to be very keen there. And if I tell you you added an alcohol here, then here the deduction would have been that a carboxylic acid is suspected to be present. Aliphatic carboxylic acid suspected to be present. You have to be very, very keen when you reach that step. So this is the example, I was talking about. So here, instead of the acid, we tell you to add an alcohol, and then later you also add what concentrated sulfuric acid. Then later you pour the contents of the beaker. After getting that sweet fruit smell, you select a esterification reaction. But instead of deducting an alcohol this time, since you added an alcohol, so we shall expect a carboxylic acid to be confirmed present. Because for you to prove an esterification reaction, that means that the alcohol that you added must have reacted with a carboxylic acid. So the interpretation is as simple as that. Now there's this rare one, which is for phosphorus pentachloride. Now this one may be beneficial for you in theory, because we rarely set it in practicals. And when you apply it, you simply see misty fumes which form dense white fumes with concentrated ammonia solution. Now here you may not give this test, and you just tell us that misty fumes which form, you may just tell us that misty fumes are formed, and you all know that that's going to be hydrogen chloride gas. So we expect such a compound to possess the OH group such as an alcohol, because in theory we only use phosphorus pentachloride to replace the OH group, which is attached to secondary or primary alcohols, or phenol itself. So you simply say that misty fumes in the observations formed, and then the deduction is that OH group attached to the substance or compound with the OH group attached, such as secondary alcohol or primary alcohol or phenol. Then same applies to dense white fumes. Now for these ones, this one is going to be rare. Maybe in mocks you may note it down, but majority of it for phosphorus pentachloride, we are going to be testing for the presence of the OH group, and this is what you should note mostly. So when you're having another reagent can be the sodium metal. Now sodium metal can be used only to confirm, just like phosphorus pentachloride, sodium metal also replaces the hydrogen atom on the OH group. So the moment we see effervescence of the colorless gas is going to be because the sodium atom is going to come on the OH group and then replaces this hydrogen, so that we see effervescence of a colorless gas or bubbles of a colorless gas after hydrogen being given off. So that's why here we are coming and saying that for the test solution you add sodium metal, and when you see effervescence of a colorless gas, I say that if you don't know this pairing or if you're not sure of it, use bubbles of a colorless gas. You may ignore the test that I place it for you. So you simply say that bubbles of a colorless gas evolved. And then you say that a compound has the OH group because it's only sodium metal that replaces this H group on these compounds. And those compounds are either going to be alcohols or phenol, or maybe the carboxylic acid because it also has the OH group. Now we also have the reagents that test different classes of alcohols, and this is a very common one. So with this one, we are going to tell that you add anhydrous zinc chloride in concentrated hydrochloric acid solution, and this is going to be nicknamed as Lucas's reagent. The reason why I'm bringing these nicknames later is because when you're answering theory papers, do not write nicknames anywhere. So the chemical name or the botanical name for Lucas's reagent is going to be anhydrous zinc chloride in concentrated hydrochloric acid. So the observation for primary alcohols is going to be no observable change. But if you're stating it in theory, you make sure that this word is included. Without this, you don't qualify for any mark. So for primary alcohols, you're going to get no observable change if at all and only if it's at room temperature. So no observable change with primary alcohols if at room temperature. This condition must be clearly seen. And then for secondary alcohols, you're going to form your cloudy solution within 5 to 10 minutes. Now, when you're in your practicals, we don't expect you to tell us this range. We expect you to tell us the specific period because you're going to provide you with stop clocks. So we expect you to provide the specific period for which you conducted or for which you saw the cloudy solution. So in practicals, you simply say that a cloudy solution formed in about 7 minutes, or it formed in about 6 minutes. You don't give us the range, but for theory, you give us the range because you didn't carry out the practical. So you simply say that cloudy solution formed between 5 to 10 minutes in theory, but in practicals, you specify the time because we give you the stop clock. You simply say that cloudy solution formed within 7 minutes. So it's as simple as that. So that is going to confirm presence of a secondary alcohol. And if at all the cloudy solution forms immediately, that confirms presence of a tertiary alcohol. So proceeding, let's look at another reagent which is going to be the iodoform test. Now here, in theory, you're not supposed to say iodoform. You're supposed to give its arrangement the way I elaborated it here. So simply say that iodine solution and sodium hydroxide solution. Now this one, the iodoform test is for compounds that contain a methyl group on the carbon atom which is attached to a functional group. If at all you're having a methyl group which is attached to a carbon atom, this carbon atom it is attached to must carry a functional group. It's going to give a positive test with this iodoform test. Arrangement of reagent is iodine solution and sodium hydroxide solution. So it's iodine solution first, followed by sodium hydroxide solution. And it tests for compounds that have a methyl group, and this methyl group is attached to a carbon atom, and that carbon atom is carrying a functional group. And they're telling that where R is going to be an alkyl group of hydrogen or any other chain. So if at all you get a positive test with it, after doing the appropriate experiment or procedure, we expect you to see a polyol precipitate. And this polyol precipitate comes with an antiseptic smell. But mainly what you're going to mark, or the mark is going to be at what you're seeing, because some of you miss out this. However, I gave also this one under the table where I summarized the smell of the products you're forming. So if you see a polyol precipitate, we expect triiodomethane to be formed. So that's the precipitate you are seeing. That's why when you're making your deduction, you start with that very precipitate. So after writing polyol precipitate formed, you say that triiodomethane formed, you just write it by formula, and then you say that therefore a compound with a structure, you draw a structure showing that we are having a methyl group attached to a carbon atom which is carrying a functional group. I hope that is clear. Now this iodoform test is going to be positive for alcohols together with carbonyl compounds because this is a carbonyl carbon group. So this carbon atom is attached to this carbon atom which is carrying a functional group. I hope that is well easier to understand. So in theory, you make sure that you summarize this somewhere else or somewhere in your notebook. Iodoform test or iodine solution in sodium hydroxide solution is going to be positive only for compounds that have a methyl group attached to the carbon atom carrying a functional group. And the positive test is going to be by seeing a polyol precipitate, and that polyol precipitate is going to be due to formation of triiodomethane. So in your deducting, you simply say that, therefore, someone may not draw the structure, and you just say that methyl group attached to a carbon atom carrying a functional group. You are going to get all the marks. So you simply say that methyl group attached to the carbon atom carrying a functional group present. You are going to get all the marks. Now proceeding, we also look at the test for amines. Now we have what we call the tertiary amines, the primary amines together with the secondary amines. So the tests or the reagents that we use to test for the different classes of amines are going to be concentrated hydrochloric acid and sodium nitrite solution. So for primary amines, you are going to see effervescence of a colorless gas. Effervescence of a colorless gas. So you may just simply say effervescence of a colorless gas. And since they are amines, the only gas we expect is going to be nitrogen. So when you see bubbles of a colorless gas or effervescence of a colorless gas, you simply deduct that it's going to be a primary amine present. And if you don't get an observable change, then that means that you are most likely dealing with a tertiary aliphatic amine. And if you get a yellow oil liquid formed, that means that you are dealing with a secondary amine. However, it's so unfortunate that this test is mainly under the theory paper 1. We give you different classes of amines, and then we tell you to give a reagent that can distinguish them, and you give the observable changes. Majority of the times we bring primary and secondary amines. So for secondary amines, we expect you to give us an observation of a yellow oil liquid formed. That's for secondary amines to be present. And for primary, we expect you to tell us that effervescence or bubbles of a colorless gas were formed together with a colorless solution. So it's as simple as that. If at all you're dealing with a phenylamine or aniline, you simply say that there's no observable change, but on warming, bubbles of a colorless gas were evolved. So you simply say that confirms for aniline or phenylamine. I hope that is clear. And please, you make sure that you share the video to colleagues so that you can all benefit as a team. Now for soda lime we rarely use it in the laboratory, but I summarize for you some of the circumstances where it's going to be applied. So one, if I do use it using the appropriate procedure, but majority of these ones, like I said, they're not going to be commonly said. So for those ones that are not going to be commonly said, you simply make a note about them according to the way I made them, and then you make some personal revision about them, so that in case they appear in your mocks, you try to find a way of tackling or making the corrections for such appropriate procedures using the information given above here. So now finally, you also pause the video and then you make short notes about the following reagents, because sometimes they also appear in the laboratory or in some mock sets and they require you to have specific knowledge about them. So you get your notebook and then you make specific notes about them. So majority of them require laboratory testing. Now, like I said, after sharing this video has been fully understood, we may try to organize we are trying to organize a practical session whereby we are going to be recording those videos together with appropriacy in using the reagents, so that you may see hands-on on how we can apply the knowledge that you have studied in implementing the techniques in the laboratory. So pause the video and you make notes about this. So that's it for this video. We'll meet in the next video under inorganic chemistry practicals. So this was about organic chemistry. We are going to cross to inorganic, and then later we shall be finalizing with quantitative practical chemistry. So make sure that you share the video to your friends and benefit as a group. So see you in the next video on the same platform.